All right, so now we're going to talk about how do we test for dichotomous variables? How do we determine statistical significance when we have essentially binary variables? So it's one or the other, if you remember, is what dichotomous means. So we've identified our dependent variable and we learn it's dichotomous. Okay, so it's based on what our dependent measure actually is. So if we care of whatever it is we're measuring ends up being a dichotomous or binary design, now we have to test that in some way. So the way you look at it is this. If both your dependent and independent variable are dichotomous, then you're going to actually have to craft what's called a contingency table, also known as a 2 by 2 table. And then the statistic you're going to use is a chi-square of Fisher's exact test, or excuse me, not of Fisher's. It's either going to be a chi-square or a Fisher's exact test. If the dependent variable is dichotomous and the independent variable actually is categorical but has more than 2 categories, then you're going to still do a contingency table, but you're going to do what's called a 2 by K, because that means you're going to have 2 rows or 2 columns, but then you might have 3 or more of the other. And so that also will get a chi-square type of analysis. So a 2 by 2 contingency table looks like this. So in this particular example, we looked at sex and we looked at what was known as pain catastrophizing scale results. So the pain catastrophizing scale is a one-page questionnaire. If you score higher than 20, then that means that you have what's called pain catastrophizing characteristics, which simply means that you are overly worried about pain at all times. Okay, it's a little deeper than that, but for this example, that will suffice. So we have a binary option here, right? So with sex, in this case, you're either female, which would be 0, or male, which is 1. For the PCS, you are either a pain catastrophizer or you're not. So if you're not, you're a 0. If you are, you're a 1. So that's where this table gets its name. 2 options here, 2 options here. Okay, so what you see, obviously, is you see a bunch of percentages as well as counts. So the way you read this is you have 18 females who are not pain catastrophizers, and you have 5 females who are, for a total of 23 females in this population or in this sample. Down here, you have 17 males who are not pain catastrophizers, and you have 10 males who are, for a total of 27 males in this sample. And then here where it says count total, so you have 35 total non-catastrophizers, 15 catastrophizers for a total of 50 subjects in this sample. And then these percentages are just simple breakdowns. So essentially what this is saying is this is the percentage within gender, and this is percentage within the PCS, and this is the percentage of the total amount. Okay, and you could just read those as is. So data being independent is an assumption of a contingency table. So in other words, everything that's in its own cell is independent of everything else in the other cells. And the cells have enough numbers in them that we consider to be sufficiently large. Okay, what that means is if you have more than 5 subjects in any cell, then that is considered a sufficiently large sample for that one item. Anything that is 5 or smaller is not considered enough. So once you get into the 2 by K situation, again, you're going to still lay it out the way you would a 2 by 2. It's just it's going to be a little longer, a little wider based on how many number of variables you actually have. So, and the type of statistics you will use are a chi-square or a Fisher's exact. Now, the chi-square is based on a test statistic that measures how much the observed data deviates from what would be considered, quote unquote, the expected data. And what do you mean by expected, you might ask? Well, the expected value for each cell in a two-way table is equal to the total in the row times the total number in the column divided by the total number of subjects. Okay, so let's look at this and we'll do the math here at the bottom. So here's our same table from earlier. And here are the expected value examples. So if we just look at, there were 35 total non-paying catastrophizers. So that's the total column times the total row. So we got to take each row at a time. So we're going to take 35 times 23. So we're just looking at the females right now. Divided by the total number of all subjects, which is 50. So in this case, the expected value would be 16 females in the non-catastrophizing group, but our actual is 18. Well, 18 is not too far away from 16 now, is it? Now, on the other hand, when we look at the males, we're going to take 35 again, so that's 35 non-catastrophizers, times 27 total males, divided by 50 total subjects, and we get 18.9 or 19. So 19 is not too far away from 17. So in this case, we would not have statistical significance. More than likely, we would still need to see what the test result gave us. But that's really how this works. So the funny thing with a chi-square statistic, however, is it's a really simple decision. It's either looking for absolutely no association between two variables, or there's some association. But the problem is that that some association, that word is used on purpose, the word some, because the problem is that the research hypothesis does not specify the type of association or the direction of it, which basically means it's going to tell you if there's a difference somewhere or some type of relationship, but it doesn't tell you where it is. And that's the scary thing about this. So you're just really just looking to see, is there a relationship in this table? Yes, but you don't know where it is specifically. So one of the assumptions of the chi-square is that you have a large random sample. And as I told you earlier, you had to have at least a 5 or better cell count for each cell that you have in your table. Okay. So for instance, when we actually run the statistic on the data I just showed you, okay, the chi-square statistic, which is listed for you right here, okay, it says that the two-sided test is a p-value of 0.239, let's just say 0.24 to round up. So that's clearly bigger than 0.05, which means it's not statistically significant. So we don't, I mean, granted, so you don't know if it's a positive association, a negative association, you don't know any of that. So right now, all we know is that there's no association between those variables. So sex and pain catastrophization, nothing, okay? Now, what were to happen if we were to use the 2 by K sample? Okay, well, in the 2 by K, this is what it would look like. We're going to stick with our pain catastrophizing variable, but now we're going to look at satisfaction. So in other words, we're going to see for a number 1, those are the people who were not satisfied. A number 2 were the people who were unsure, and a number 3 were the people who were satisfied. And so we look at satisfaction and catastrophization. And so in this particular case, what we're just by eyeballing the data, we actually have examples here where we actually have 3 and we have 2 in some of these cells. So based on what I just told you, that means now we cannot use the chi-square. We have to use what's called the Fisher's exact. So when we go to the output, what we have to look at is not here where it says chi-square. We actually have to go down here to where it says Fisher's exact test. So here's Fisher's. We come all the way across to where it says two-sided, and we have a very, very low p-value. So this is clearly lower than 0.05, which says we have an association. We just don't know where. So as a summary, when you have 2 dichotomous variables, you're going to do a 2 by 2 table, and based on the number of individuals or number of responses in each cell, then you are going, if it's 5 or greater, then you can use the chi-squared. If it's less than 5, you have to use the Fisher's exact test. If it's a 2K setup, the same rules apply. Thank you.
Ang pagiging champion, nakukuha sa araw-araw na pagpupursige. Kaya araw-araw mag-Milo. May milk. Multivariable.
In Unit 4, we're In Unit 4, we're going to talk about one-way and two-way ANOVAs. When it comes to research in the field of business, economics, education, psychology, etc., the analysis of variance, shortly known as ANOVA, is extremely important. This tool is a very common analytical tool and technique employed by researchers to make a comparison between more than two populations and help in performing simultaneous tests. A one-way ANOVA involves one factor accounted for, while a two-way ANOVA accounts for two factors being investigated concurrently. In a one-way ANOVA, the researcher takes only one factor, while in the case of a two-way ANOVA, the researcher investigates two factors at the same time. For example, in a one-way ANOVA, a researcher may be studying how background noise affects the way students learn. In a two-way ANOVA, however, a researcher may want to determine whether the brand of laundry detergent used and the temperature affects the amount of dirt removed from laundry. So it's a much more complicated experiment involving multiple variables. A one-way analysis of variance involves a hypothesis tests where only one categorical variable or single factor is considered. It's a comparison of means of three or more samples. If it were simply two samples, you would use a t-test. It finds the difference among different categories which have several possible values. And a null hypothesis is that the equality in all the population means, and a directional hypothesis is that there will be a difference in at least one mean. This is commonly used by educational researchers, in Unit as well 4, as we're going to talk about one-way and two-way ANOVAs. When it comes to research in the field of business, economics, education, psychology, etc., the analysis of variance, shortly known as ANOVA, is extremely important. This tool is a very common business, psychology, etc. There are several assumptions inherent to ANOVAs. First, the normal distribution of the population from which the samples are drawn. Second, measurement of the dependent variable is at an interval or ratio level. Third, two or more than two categorical independent groups in an independent variable. Fourth, independence of samples. And fifth, homogeneity of the variance of the population. In a two-way ANOVA, as its name signifies, a hypothesis test wherein the classification of data is based on two factors. For instance, The two bases of classification for the sales made by the firm on the first on the basis of sales by the different salesmen, and second by sales in various regions. It is a statistical technique used by the researcher to compare several levels of the two independent variables involving multiple observations at each level. Two-way ANOVA examines the effect of the two factors on the continuous dependent variable. It also studies the interrelationship between independent variables influencing the values of the dependent variable, if any. And it involves a hypothesis test wherein the classification of data is based on two factors and examines the effect of those two factors on the continuous dependent variable, as we've said. The two-way ANOVA assumptions include a normal distribution of the population, measurement of dependent variable at a continuous level, two or more categorical independent groups in two factors, categorical independent groups that have the same size, independence of observations, and homogeneity of the variance of the population. If we look at a comparison between the one-way and two-way ANOVAs, the differences typically lie in the fact that you're dealing with two independent variables in a two-way ANOVA. Also, in the compares row, you can see that for a one-way ANOVA, levels of one factor, and on two-way ANOVA, it only has to be the effect of multiple level of two factors.